So thank you, Marie. Hello, everyone. As most of you already know, my name is Victoria Mingote. I'm a postdoctoral researcher since 1 year ago from the University of Zaragoza. And in this talk, I'm going to explain several interesting approaches, well, just an overview of them, that I carry out during my PhD in which these approaches are focused on two main streams of research for face and speaker biometric systems. The first part of this talk is about representation learning, and the second one is based on different metric learning approaches. But before to start with them, I'm going to briefly explain the motivation and how began this work. Nowadays, as already you know, biometric recognition systems have become a crucial part of our daily lives, using them for different applications. The expansion of these kind of systems has promoted a great development of the technology behind them, especially with the spread of AI algorithms. However, there is still some issues that has to solve when it has problems, when limited data is available, and when we want to transfer techniques from a specific task to another one. This last issue was the starting point of this work, because at the beginning we developed several face verification systems using this typical structure of systems based on DNNs. To evaluate these systems, we employed a small video dataset called Movio dataset, where we achieved good performance, especially when we increase the number of layers. So in view of these results, and also we knew that for test-independent speaker verification systems, similar architectures were used successfully, we decided to introduce them to create a text-dependent speaker verification system. At this point, I want to make an important remark, because you all are familiar with the speaker verification, but probably the speaker verification that you have in mind are test-independent. So I mean, in this kind of systems, the target person can say any sentence, and the system grants the access. Nevertheless, in the case of test-dependent speaker verification, a fixed passphrase has to be pronounced by the speaker to grant the access. So in any other case, the system has to deny the access to the system. So this protocol has an advantage that it gives more security to the system, but also has the disadvantage that it's more complicated to get this kind of data. So therefore, coming back to the previous architecture, we did some modifications over it to use for test-dependent speaker verification systems. And we evaluate the performance of our systems using a text-dependent speaker verification dataset, which is called RSR 2015, and also note that the dataset is quite small. So here we can observe the result that we achieved, where we found that these kind of approaches do not perform well for these tasks, regardless of the network depth. So we say this since we knew that for this dataset, traditional approaches as HMMs or GMMs exhibit equal error rates values, the lower the better, around 1%.
So when you have a basic speaker verification system, I know what equal error rate means. It means you have equal numbers of false rejections and false acceptance. But here there are two kinds of false acceptances, right? You might accept the correct speaker saying a wrong phrase or an incorrect speaker.
Both.
So do you know the breakdown? I mean, which is the harder of the two? Is it, for example, which is harder, the correct speaker saying the wrong passphrase or the imposter saying the correct passphrase?
I guess we don't analyze the numbers.
Okay.
But the owner of the database can answer the question.
Yeah, actually, I've been working a bit on the topic. Actually, it's usually more difficult. Well, it depends on the system you're using first, of course. If the more ASR you put in, the easier it is to discriminate between one speaker pronouncing 2 sentences. But usually for speaker verification, all the systems we're using are better at discriminating between different speakers than different text. And but definitely the most difficult is the same speaker pronouncing something different or something even close.
Also, I'm going to show an illustration now that shows a cosine similarity matrix where we analyze a bit this, but not with numbers, just in an illustration. So, hence, we decide to make a deeper analysis of what might be happening, and we compute, as I was mentioning, and depict the cosine similarity matrix of 2 different speakers pronouncing different phrases. So in this figure, we observe that in the diagonal, we have high cosine values for which shows the same speaker pronouncing a different phrase has a good behavior. But in the other hand, we also have a high similarity between different speakers pronounce the same phrase. So this could be one of the reasons between the others that Anthony mentioned about the poor performance of the system. So once we did this analysis, we conclude that a possible cause of the previous inaccuracy could be derived from the use of the global average pooling that is usual to use in this kind of systems, to obtain the final representation of the utterance. Since this pooling mechanism mainly keeps the information of who is speaking, and it may not capture correctly the phonetic information. So therefore, the order of the phonetic information may be neglected, and this is a relevant part in the identity information, as I mentioned, for the test-dependent speaker verification process. So, to solve this problem, we propose to replace the global average pooling by with a differentiable alignment mechanism where the alignment matrices are obtained externally, where with the information of the similarity between the different time frames. And after that, can be included as an internal layer, a new internal layer in the system. The combination of the DNN with this new mechanism allows to keep the temporal structure of the utterance. And also, thanks to the use of this alignment mechanism, the architecture is able to encode the phrase and speaker information in a representation vector which has a similar behavior as the supervectors in the traditional speaker verification. And also, we can use different alignment techniques, but in this work we use HMMs and GMMs. Therefore, here I saw the architecture was proposed, which includes a phonetic alignment mechanism as a key component to obtain this representation vector instead of using the global average pooling. And this new approach was tested using the same dataset as I already mentioned. And here, apart from the numerical results in terms of equal error rate, I think it's more interesting to see these representations that we did of the global average embeddings and the neural network supervectors in a 2-dimensional space. So in this first figure, we represent the global average embeddings, and we can observe that it's not able to separate the representations of this kind of representations. Yes, 30 degraded colors, not only one for each speaker inside of the. There's one speaker and there are 30 different phrases and each color is one phrase. Yes. So while in the case of we included this alignment mechanism, we observed that a huge decrease in the equal error rate is achieved. And also, we observe pretty well each cluster of these 30 phrases. And then the speakers inside of each cluster is a different color also, in the same tonality. So, on the other hand, during these different experiments that we carry out during the previous systems, apart from the issue that I already mentioned about the phonetic information, we found that there are still some problems in these kind of systems when limited training data is available, such in RSR 2015, such as the lack of ability to properly generalize to unseen data and the overconfident predictions produced. So to address this problem, it has been proposed different alternatives. One approach to solve this problem is the use of an architecture which follows the philosophy of knowledge distillation. This approach consists on training two neural networks where the student network is trained to mimic the target predictions from the teacher network using the Kullback-Leibler divergence. An important point to remark here is that in most of the previous works that we found with this philosophy, the teacher network is pre-trained and the weights are frozen, so to reduce the complexity of the model. But therefore, the student has to learn during all the training process from the same labels, fixed labels. However, in this work, we propose a slightly modified approach of the knowledge distillation in which the teacher network is trained at the same time as the student network. Besides, we adding some noise at the input to give more variability to the different input signals. And in this case, we use the random erasing technique for this. And therefore, with this new approach, the teacher network produces different prediction labels during the training progresses. So, and it allows to better capture the variability on these labels for the student network. So now here we can see this architecture with the two neural networks, where the teacher network is trained to train as usual using the cross-entropy laws, while the student network is trained to minimize the difference between the prediction labels from the teacher network and the student prediction labels. So we evaluated here and see how this teacher-student architecture behaves using it with the alignment mechanisms of the HMMs and GMMs. And we observe also a huge relevance improvement when we combine it with the GMM alignment mechanism, which is a more flexible approach. So motivated by all the problems that I already mentioned several times, we follow looking for other alternatives to use to solve them without the need of an external alignment mechanism. So we propose the introduction of the multi-head self-attention mechanism, which exploits the phonetic knowledge needed for the text-dependent speaker verification. So moreover, this mechanism is based on multiple dot product attention that which are doing in parallel. So therefore, with each head is focused on different positions of the sequence and provide different relevance to some parts of them to discriminate better between speakers and utterance. And also mention that once this multi-head self-attention layer is applied, a feed-forward usually is applied to transform and process the vectors before the next dot product attention layer. Nevertheless, in our architecture, we propose to replace this feed-forward layer by memory layers which allows to improve the model capacity with an insignificant computational overhead. And this is possible since these kind of layers are able to store the knowledge that the network is learning during the training process. So therefore, there's some missing parts. And therefore, using this architecture with the approaches explained just before, we achieve promising results thanks to the powerful of the self-attention mechanism without the need of including any external alignment mechanism. Despite that this kind of approach usually use a global average pooling to obtain the final representation vector, which has some problems, as I already mentioned. So we propose one step more to address this issue. And we introduce a learnable vector known as class token. To introduce this vector into the previous architecture, we have the class token is concatenated before the input of the first MCA layer. And the state at the output of this class token is the vector that is employed to perform the class prediction. So with this approach, the self-attention is forced to capture the most relevant information with the class token simulating as a global Lutherans descriptor, similar to the supervector approach that I mentioned at the beginning, since the matrix of self-attention weights plays a role similar to the alignment matrix in the alignment mechanism. So motivated by the success of the teacher-student SONS preview, we present a new approach introducing this teacher-student combined with the last approaches of MCA and the tokens. To test this new approach, we use the same dataset as previously, and also we introduce a new test-dependent dataset, which is larger and called DeepMind. And in both cases, we can know that relative improvement achieved is relevant when we use these tokens instead of using the global average pooling. In view of the relevant results obtained, we also conduct an analysis to explain where the matrix of attention of these tokens is focusing on these two utterance which are the same phrase pronounced by different speakers. So there are in the first row, there are the two utterance, and the second one are the self-attention weights, and the third one are the sum of the previous attention weights. So note that since these figures are of the same phrase, self-attention is focused is focused on the same areas, but different relevance is given to each of them. And moreover, we can also see that the weights do not pay attention to the areas at the beginning and at the end of the sentence, which corresponds with moments of silence. So this is the end of the first part. So along the first part of this talk, the different representation learning approaches that I presented were trained using the traditional cross-entropy laws. However, in the second part of this talk, I'm going to present 3 new loss functions oriented to the goal task that we develop in this work. So we're mentioning here that ideally verification systems based on DNNs should be end-to-end to carry directly the verification process as a binary classification. Nowadays, existing a few approaches with this philosophy, but in many of the current systems, as we did in our previous systems, the usual way to work is training a DNN for multi-class classification, and after that, a backend is applied over on the embeddings. So one of the most common backend is a triplet neural network, and this kind of network is composed by 3 instances of the same net with shared parameters. And also it's important the way to select the input to this kind of approach. So because you have to select an example of a specific class, which is called anchor, another example from the same class, this is a positive example, and the third one from a different class, so it's the negative. And in most of the existing systems with this kind of approach, the cost function employed is the triplet loss. Nevertheless, this loss is not oriented to the goal task. For that reason, we propose an alternative to that. So to make the training procedure more consistent with the final evaluation procedure, we propose an approximation of the AUC loss. And this metric can be expressed, as we can see, with using the one logic function. But also, this metric can also be expressed using the unit step function. However, this function is not differentiable, so we have to make an effective approximation to enable the backpropagation of the gradients during the training process. So we substitute the unit step by a sigmoid function which is differentiable. So this approximation allowed us to include this new loss function for the triplet neural network instead of using the previous triplet loss. And as I mentioned in the previous slide, also is important the way to select the triplets to train a good system. So we also include in this work a smart strategy selection, which is called hard negative mining selection. This intelligent selection process involves the selection of the anchor negative and anchor positive pairs more complicated to determine correctly by the network. So here is the system developed to evaluate the effectiveness of this new loss function, where it's composed of two different architectures. The first one that I presented in the first part of the talk. And once this architecture is trained, we introduce the backend part. So as we did in the first part, we depict these representations in a two-dimensional space to analyze the effect of applying now the backend. So here we can observe the same two representations that I saw in the first part. And in this third figure, we saw that the ability to discriminate is even better when we apply our triplet neural network with the AUC loss proposed. So apart from applying it for test-dependent speaker verification tasks, this approach was also applied for the face verification task. So here, as in the case of the speaker verification, we use a similar architecture, and we evaluate it using a Movio dataset again. So these results confirm the conclusions that we extracted in the previous task, where we can see how applying this backend improves the whole performance in all the different data and with both architectures that we use. And finally, after probing the x-axis of this proposed backend for speaker and face verification, we also introduced this approach in the language recognition task to discriminate better between different, similar languages. So here we can see a recap of the results of the backend using the language recognition evaluation datasets. And we saw that the results are improving in two of the three datasets, especially when smart training strategies are applied. So we can conclude from this this work that we did here that it can be applied for different verification tasks and other tasks, as Pablo mentioned later. So the previous AUC loss has shown that this is a good choice to improve the overall system performance using this loss function oriented to the goal task. Nevertheless, this kind of approach with triplets have some drawbacks, as the need of smart strategies to create these triplets, which has high computational cost. So therefore, we have continued investigating different alternatives to train these systems, taking advantage of the efficiency and the speed of multi-class training architectures. While at the same time, the system is trained with a different verification metric. So to develop this approach for training multi-class architecture, we propose the implementation of an approximation of DCF as a substitute for traditional cross-entropy loss. The DCF metric is more suitable for the verification task, since it's inspired by one of the main verification metrics that we use to evaluate the system. And this metric measures the decision errors caused by false alarms and misses. And also, as in the case of the AUC, these theoretical equations, are not non-differentiable. So we follow the same process using the sigmoid function to replace the binary counter. So these expressions are the differentiable version of the previous one, and doing a combination of them, a weighted combination of them, we have here the loss function that we are going to use. And you maybe ask, why do it in an efficient way? Well, we calculate both terms, obtaining directly the scores from the last layer of the DNN, and assuming that during the training we have one target example, and n, the total number of identities, minus one non-target examples. So this assumption is possible thanks to the interpretation of the last layer of the DNN as an embedding of different training speakers. So the system employed to check the new loss function is the same as the previously I presented with the AUC loss, but the main difference is that for using for ADCF loss, we only need the first architecture. But in this case, we keep the second one to compare the effectiveness of the method. So we can observe that architectures C trained with the new ADCF loss obtains the best results. Especially relevant is the comparison with the improving comparing with the cross-entropy loss and the angular softmax, where are both the most comparable trained with the most comparable strategy than the one that we present. So to finalize with this metric learning part, we propose a last alternative loss function to train the multi-class architectures. The previous ADCL loss, as I show, has a great potential to train this kind of architectures with a loss oriented to the task to minimize the DCF. However, this loss has also some drawbacks since it's an application-dependent metric and needs some prior and cost parameters assumption. Moreover, we also had to make an approximation to be able to train the neural network. Therefore, we propose another alternative verification metric that can be used in the same philosophy of the DCF, but this metric is application independent. So this other main verification metric is the log likelihood ratio cost function, and we implement it to substitute the cross-entropy and also our ADCF loss for training the multi-class architectures. CLLR is a generalization of the DCF since it's formulated as the integral over all the possible operating points. So this loss measures the expected cost of target and non-target samples. Both expressions are combined to minimize the CLLR as objective loss in our network. This expression is an analytical closed form expression presented in the literature to solve the previous integral. So in this case, we did not to make any approximation as we did in the DCF case. So to evaluate this new proposal, we employ the first architecture with the MC layers that I presented at the beginning. And in this architecture, we introduce the new loss function and also the previous ADCF and other loss to check the difference. So here, to finalize, this is the results that we obtain with where we can see that the proposed objective loss outperforms all the alternative loss functions used to train these systems. So to finish this talk, here there are the main conclusions or remarks of the different approaches in the two streams of research. In the first one, as I mentioned several times, the relevance of keeping the phonetic information for test-dependent speaker verification tasks, especially when you have limited data, to discriminate better between speakers and utterance. And so for that, we presented several approaches oriented to keep this information to improve the generation of signal representations to the final verification process. And on the other hand, these kind of approaches that I presented at the beginning were not designed to optimize the verification task itself. So we also propose successful new training losses based on the final verification metric as AUC, DCF, and CLLR. And that's all from my side. I only want to say that I skip a lot of details and experiments, so if you are interested, you found interest in one of them, you can check in the articles that they are published. And also my thesis is publicly available, so you can check more on it. And that's all. Thank you for your attention.
Any questions?
I don't know. How many?
Thank you very much. I had two questions. The first was, what is the motivation or what are the kinds of applications where you would do text-based speaker verification as opposed to just plain speaker verification? And the other question is, you mentioned language verification, which I hadn't heard before. Is that different from spoken language ID?
Well, for the first question, this work also started because we have a project with a company that is using this kind of test-dependent speaker verification systems for a bank application, if I don't remember wrong. And also nowadays with OK Google, you have to verify that are you saying that sentence. So it's also an important for other companies, I guess, at least. And the second one, I was speaking about the language recognition evaluation data that are proposed by the NIST. So it's verifies if the utterance is from one language or other. So it's the spoken language, it's language identification at the same time.
Yeah, thank you. And just a quick question about the attention mechanism that you use. Did you try on text-independent verification? Because that one question I think we already discussed with Temos in a previous presentation is the using this information and maybe also using an attention mechanism which is not self-attention but coming from some ASR or some other kind of system.
No, I didn't check it. I moved to other topics last summer and during the last month, so this was my last work, and I finished at just before defending my thesis last May, so I didn't check it. It's an interesting thing to check. Yeah.
Yeah. So I had two questions. One was about when you had the external segmentation followed by the text-dependent verification, you're trying to do phonetic segmentation, and then later on you replaced it with this attention mechanism. Now I was thinking that a lot of speaker-specific information is not just in the phonemes, but in fact in the phone transitions, in the diphone statistics, if you will. Do you know if your attention mechanism is using the same kind of segmentation as phonetic, or is it focusing on the transitions? Do you have any insights on what it does?
I guess most of the information, I guess, is also in the way that the person is speaking, so in the transitions and the onsas and the codas, but I don't check it with the details. So.
My other question was about DeepMind. We were not able to get that data set in the US. How did you get it?
Oh. After a lot of problems with the network in Iran, because they have some strikes and the network was down, and a lot of emails with Hussein. Well, in Spain is... I don't know, I just send emails with Hossein and Senali, and I achieve it. Well, I don't know if something is also involved with the BUT, I don't know, and so maybe it's... I don't know, maybe this question he knows better than me.